Wind power, how moving air becomes electricity. In episode 1, we learned that energy never disappears, it only changes form. Wind power is the clearest example of that idea in the whole energy world. Here's what happens inside every wind turbine on Earth in 3 steps. Step 1. Moving air carries kinetic energy, the energy of anything in motion. You can't see it, but on a windy day, it's enormous. Step 2. The blades convert that energy into rotation. Turbine blades are shaped exactly like aircraft wings. When wind flows across them, a pressure difference forms. Lower pressure on one side, higher on the other, and that difference pushes the blades around. Wind becomes spinning motion. Kinetic energy becomes mechanical energy. Step 3. A generator converts that spinning into electricity. Coils of wire rotate inside a magnetic field, and that motion drives electrons through a wire. The last step is identical in a coal plant, a nuclear plant, and a hydroelectric dam. What is always different is what turns the shaft. Here is the wind. Wind to rotation to electricity. 3 steps, no fuel burned, no carbon dioxide released. Now here's where the math becomes surprising. If wind speed doubles, the energy doesn't double. It goes up 8 times. And if you double the blade length, you capture 4 times the power. Every extra meter of that blade is worth a very large amount of electricity. Not a little more, but exponentially more. That is why turbines keep getting bigger. Not ambition, math. Today, we look at the physics behind this, why height and location matter so much, how China became the world leader by understanding these laws better than anybody else. Height is everything. That math that plays out in the real world is one of the most direct ways possible. Height. The higher you go, the faster and steadier the wind. And faster wind means exponentially more power. This is why countries that seem to have ordinary winds can still build successful wind industries. Germany has no exceptional wind resources, but German engineers built towers over 160 meters tall to clear the treetops of their forest and reach steadier air above. Texas, in the central U.S., sits in one of the windiest corridors on the continent. Its turbines are tall enough to tap winds, but almost never stop. In China's Inner Mongolia, a vast flat region far from any coast, the winds at ground level seem unremarkable, but at 140 meters, they're strong and remarkably consistent. Inner Mongolia alone now generates more electricity from wind than the entire country of Germany. Every country has learned the same lesson the same way. Build higher, get more. Onshore versus offshore, the trade-off. The same mathematics also explains why so many countries are pushing their turbines out to sea. Offshore, the wind is stronger and steadier, and with no roads to limit the size of any parts arriving by ship, engineers can build their largest blades there too. Faster wind and bigger blades, both laws working at once. And because offshore turbines are kilometers from shore, almost no one can see or hear them. The results across different countries are striking. The United Kingdom now generates more than 40% of all its electricity from wind, mostly from offshore farms in the North Sea. Denmark regularly produces more electricity from wind in the single day than the whole country actually needs, and sells the surplus to Germany and Norway through undersea cables. The Netherlands is building some of the largest offshore wind farms ever attempted, aiming to power most of the country by 2030. China has built vast offshore arrays in the East China Sea and Bohai Bay, thousands of turbines stretching to the horizon. Countries that started later are now catching up fast. The US opened its first large commercial offshore wind farm only in 2023, but several much bigger projects are now under construction along the Atlantic coast. Offshore does have one serious weakness. It costs 2 to 3 times to build and maintain than onshore. Salt air corrodes metal. Undersea cables are expensive. Every repair requires a ship, so most countries run both. Onshore, where land and wind allow it. Offshore, where they need more than the land alone can provide. The limit no engineer can engineer around. Like solar panels, wind turbines have a physical ceiling. A turbine can't take all the energy out of the wind. If it did, the air behind it would stop completely and no new wind could flow in. Physicists worked out that the max energy any wind turbine can extract is 59.3% of the wind's energy. This is called the Betz limit. Modern turbines reach about 35 to 45% in real-world conditions. Impressive, but always below that ceiling. How China became the world leader in wind. In both 2023 and 2024, China installed more new wind capacity than every other country on Earth combined. The largest turbine in the world, the MYSE-20MW, was built by a Chinese company. Its rotor measures 310 meters across, 3 full-sized football fields laid end to end. How did China get here? The same pattern we saw with solar panels in the last episode. Ambitious government targets created massive domestic demand. Manufacturers built at an enormous scale, learning and improving with every batch. The same Wright's law dynamic. Costs fell, quality rose, and China ended up leading the world. The one thing even the best wind farm can't fix. Wind power story. At its core, it's a story about physics, mathematics, and scale. The bigger the turbine, the taller the tower, the stronger the wind, the more electricity you get. Not just proportionally, but exponentially. Engineers have spent decades learning to capture that math in steel and carbon fiber, reaching higher and higher into the sky. But even the best wind farm in the world has one inescapable weakness. Sometimes the wind simply stops. When it does, where does the electricity come from? That question we will answer in the next episode. If you could design a wind farm anywhere in the world, on land or at sea, where would you put it and why? Tell us in the comments.